Okay, we are used to rectangular equations. Rectangular equations, you get x, y coordinates, find an infinite amount of them, you can graph them, and they make these nice two-dimensional graphs. Quick example, y equals negative x squared plus 4x. Typically, we're taught to plug in x's, and we'll get y's. This is like back in algebra. You get 1, 3, 2, 4, 3, 3, and 4, 0. And you could plot those points, and then you can say, oh, well, are there more solutions? Yeah, of course. There's an infinite amount of solutions between any of these 2 points, and the collection of the infinite amount of solutions makes this two-dimensional graph, and that's great. However, we don't know when the solutions occur. There's no time element to this. It's just solutions. We like to go left to right. That's because it's just easier to go left or right. We like to start at smaller values and go to large values, but we can't really associate a direction or a when to this situation. But we did address whens with other situations, like with straight line motion problems. Okay, now what do I mean by straight line motion? That means we're talking about one thing, an object, on a one-dimensional line. Okay, like all of a sudden I can change it. Instead of y equals x's, I can say x of t is equal to negative t squared plus 4t. And then I'd have the same kind of points, but it would not be an x and a y. It would be at a time, what is my position on a one-dimensional axis? So I went like this. And this would be, the same graph. However, it would be showing you not an x coordinate, but at what time am I at when I'm at a position on my one-dimensional axis. So it's like we start with a particle. Let me make it a red particle, or an object. And at time 0, there's my object on this one dimension. Then at time 1, we moved over to 3. Then at time 2, we moved over to 4. We would find that would be when the particle was at rest, when the velocity of the particle would equal 0, because you can look at the tangent, and the derivative of position would be velocity, and we could say, oh, okay, my particle's at rest at time t equals 2 and my position's 4. But then all of a sudden, we would start moving to the left. And this would be when t equals 3, and this is also when t equals 4. Okay, so now I moved right and I moved left, and I have time associated with a position. But this is only in one dimension. This is not great. This is fantastic, but a lot of things move in 2 or 3 dimensions. Well, let's not get too crazy and go straight into 3 dimensions. Let's stick with 2 dimensions. What can we do to express something that moves in 2 dimensions, but that has some time associated with it? Well, we have these parametric equations for that. If you've taken physics C or just physics in general, you are comfortable with these parametric equations, because you will be given 2 equations, all associated with one variable, the parameter or time. Okay? 2 equations with 3 pieces of information to make one graph. Let's look at just a simple one. I'm going to just switch this to x of t equals t, and y of t is equal to negative t squared plus 2t. We are looking at both of these simultaneously. We call t the one variable that is going to help us express x and y as the parameter. It is the thing tying everything together. Most of our parametric equations will use t, though you do not necessarily need t to be the parameter. And all of a sudden, what we would start with is time. Actually, I'm going to move it back to 2t, just to make it obvious. And time would be the independent variable. And our x-coordinate and our y-coordinate would be dependent on whatever the time was. So I plug in 0 into x of t. X of 0 would give me 0. Y of 0 would give me 0. I now have a point on an xy axis that is 0, 0 when time is 0. So all of a sudden I have this third piece of information like I did on my one-dimensional axis, but now we're on a two-dimensional axis. Now it doesn't really look great because we're at 0, 0, 0, but let's look at when time is 1. Well, x of 1 would be 2, y of 1 would be 1. So all of a sudden now I have the point 2, 1 right here, which is at time equals 1, which means I'm traveling starting at this point to that point. There is a direction. I can kind of denote that direction using an arrow. I went from here, I started here, I moved there. Now if time is 2, I have 4, and this also is 0. So at t equals 2, I've now moved from this point to that point. I've traveled in this direction, and now I have some time associated with my location. And let's just do 3. I would be at the point 6, and this would be -9 plus 6, -3. Down here, I now have moved from this point to this point, and that's the time in which I got to that point. Okay? 3 pieces of information, not only giving us location, x and y, but when are we at that xy? Okay? This is motion now in 2 dimensions. All right. Well, go ahead and practice graphing a parametric equation by hand, denoting the direction and listing a few points. Now, to do this, what I would recommend is just to start with your 3 pieces of information, your independent and your 2 dependent variables. Pick some times, 0, 1, 2, 3. Grab some points, and then plot those points and make sure you denote the times at those points and also indicate direction in which you've traveled from point, at t equals 0 to point t equals 1. Okay, go ahead and go ahead and do this one. Now here we're not starting at 0, 0, 0 like the previous one, which was just different. I wanted it to look more like the rectangular one. We're starting at 5, -3. So this is my starting location when time is 0. I then move to position 3, -2 when time is 1, which means I'm moving to the left and up between 0 and 1, which you can see visually, and we'll also figure out another way we can see the direction that we're moving. Then we travel to 1, 1. So again, still moving to the left and up. So there's my direction. This is when time is 2, and then we get to -1, 6. When time is 3. All right, pretty cool. So we start here, we travel up and to the left if this object's position in 2 dimensions was given by this set of parametric equations here. Now what's cool is that your calculator can also do this. Okay, everybody get a calculator out. Sometimes it's helpful to graph it with your calculator. Most of the times you won't need it. But it can be used. Now you think, okay, I go in the y equals, and I always get y equals. But I can change the mode of my calculator. And instead of rectangular, I can switch it to parametric. So this is like function mode, y in terms of x's. I can go down to function and slide it over to par, press enter, and go back into y equals, and all of a sudden you got x sub 1, y sub 1, x sub 2, y sub 2. This is where we would type in parametric equations. Let's go ahead and see the previous one, 5 minus 2t and t squared minus 3, just for fun. Now what's awesome is that this x button here, why hasn't it just been x? Why is it x comma t comma theta comma n? Because it depends on your mode. If you press this x button right now, what do you see? T pops up. Okay? It's because we are talking about things in terms of t being our independent variable. So that's why it's not just x, because it's all about our mode. 5 minus 2t, and then t squared minus 3. If things are set up, excuse me, well, we can immediately see what it looks like. But it kind of all depends on things. If you go to your table, you'll be able to see that it looks like we're starting at 0 and then going time 1, 2, 3. And we get our x coordinate and our y coordinate all at once. But sometimes we won't want to start when t is 0. Sometimes you can think about going like back in time. Like t is 0 is now. Well, t of -2 is back there. If you change your table set, you might want to say, hey, start at -2. But if you graph, it doesn't change anything, but you can see in your table, it's now starting at -2. What you could do is go to your window and tell it a minimum t to start with. So instead of going from 0 to what looks like 2 pi is the basis, you could say, let's start at -2. And all of a sudden, my graph kind of expands. And you said, oh, if we went back in time to t equals -1 and t equals -2, I'd start here and then travel down and to the left until here and then up from there. Isn't that interesting? I think so. So let's go back to 0. And this is our graph starting at 0 to 2 pi. Why did they choose 2 pi? For certain situations with cosines and sines. Let's go ahead and graph and see what these look like. t squared minus 1 and t plus 2. What will that look like? Doesn't look that nice, right? Just kind of going up and to the right, starting point there. But maybe if we change our window, maybe go back in time from -6, we can see this kind of sideways parabola. Okay? Let's look at cos t plus t sine t. Again, I'll start with my window at 0, and then I'll just kind of adjust it. I see I have what looks to be a curly Q. It kind of stops. Why does it stop there? Well, because it's telling a calculator to stop when t is 2 pi. Well, let's just kind of expand things. Excuse me. Let's go from like -6. See what that looks like. Whoa. Okay. Well, now we see we started, I don't even know where we started. It started here, made this little curled around. We can maybe expand it even more from -10 to 10. And you'll start seeing that some really cool, okay, this is our starting place at -10. Back 10 seconds in time. Awesome, and if you continue to expand, you'll continue to get these really cool looking graphs depending on what the parametric equation is. Where was it? Here to here to here and back out. All right, so it's really cool stuff. And it's just describing a two-dimensional motion of an object, okay? Now, something that you will be required to do sometimes is to convert these parametric equations to rectangular equations. Sometimes it can help you with a problem. Sometimes you can check things out. But this is called eliminating the parameter. So we turn in x comma y equations into a y equals x equation. Now, in your examples, on page 1, you will see this problem. We are kind of eliminating some homework questions. Okay, so go to your examples on your packet. And most of our examples will be coming out of this packet. So we are asked to make a table of values, sketch the curve, indicate the direction of your graph, then eliminate the parameter. Do not use your calculator. We're going to skip the part 1 and 2. I'm going to leave that to you. But I'll show you how we can turn this into a y equals x equation very simply. All we need to do is solve the x equals equation for t, and then sub that into the y equals equation. Let me show you that. I can take x equals 2t plus 1, make it x minus 1, which equals 2t, or t is equal to x minus 1 over 2. And then I will take what t is equal to, substitute it in for y, and I get y equals x minus 1 over 2 minus 1. If I wish to simplify that, I could maybe multiply the top and bottom of this by 2, making it y equals, this will be 2 over 2. X minus 1 minus 2, which would be x minus 3 over 2. Or even go further and say it's y equals 1/2 x minus 3/2. Okay? Which I could have, gotten to a different way. And I get that rectangular equation. Well, let's see. I'm going to go ahead and graph this rectangular equation. You guys graph this using the parameter mode, and let's see if our graphs are going to be the exact same. I go back to rectangular, 1/2 x minus 3/2. Obviously a straight line. Let's see, do you guys see the points? 0, negative 1.5, 1, negative 1, 2, negative 0.5. Are those in your table? No? 1, negative 0.5 is not in your table? That 1, negative 1 is not in your table? Yeah. It is? It's not. Mr. Buckner, you say it is? Well, what's going on here? When time is 0, we should have 1, negative 1. Right. So you see it, Mr. Darnell?
I didn't have like negative 1.5. I have 1 negative.
Oh. Well, did I mess up at all? But you don't have, you're saying you don't have the point 2, negative 0.5? Well, it's probably because time is off. So you have 3, 0. All right, 3, 0. Okay, guys. Good. What other points do we have? 5, 1. Okay, good. So I graphed the same thing as you did. But what you have is time and direction. What I have is just an infinite collection of points. You have a starting point and an ending point. I have an infinite collection of points for a domain of any x, okay? You don't have any x. For this, we'd have to denote this as, oh, well, if we're starting for t is greater than 0, well, or greater than or equal to 0, that means my x is going to have to start from x is greater than 1, right? All of a sudden, my domain kind of shifts. And if I graph this rectangular to graph this, I would start at, the 1, negative 1, and then go up from there. Okay? So just showing you can get that. Why don't you go ahead and, for number 3, eliminate the parameter to turn that into a rectangular graph. Sometimes it helps you at least understand what the graph should look like, though graphing parametric equations are not too difficult. Okay, we should get y equals plus or minus root negative x plus 2. Now, depending on what the t values we're going to use, we would either see all of this, which is your sideways parabola. If t was restricted to just like positives or starting at 0, well, I know I'd start at a value 2, 0, so that means x would start greater than 2. Okay? So if t was greater than 0, you'd say, okay, let's just graph this, but x's are going to be greater than or equal to 2. Okay? That's all if the domain is restricted. I was going to do 5, but let's just skip it. All right, let's talk some calculus. Let's find the slopes of the tangents to these parametric equations. Okay? Now, typically we get a y, an x equals, and a y equals. But we're trying to find dy dx. Okay? How can we find dy dx? And these are always in terms of t's here, at least the ones that we're going to do. Some version of t's for x's, some version of t's for my y's. Okay? Again, remember dy dx. Why dy dx? Because it's slopes. slope, change in y, change in x. This is instantaneous change in y over instantaneous change in x. Now, if I were to take the derivative of this, I would not take the derivative with respect to x, because that would just give me 1 equals dt dx. It does not look nice, 1 equals dt dx. It's not going to necessarily help me. So what I am going to do is actually take the derivative with respect to t, because it's x as a function of t's. So I'm going to d dt this. And all of a sudden, we would get dx dt is equal to something. And if I took the derivative with respect to t of y, I'd get dy dt equals some stuff. Well, watch what happens. If I manipulate the dy dt and the dx dt, I can get dy dx. What can I do to dy dt and dx dt to turn it into dy dx? Any guesses? What operation can be done with these to create this? Cross multiply? That's kind of for solving equations. I'm thinking like, can I add them together? Can I multiply them? Can I divide them? Can I just subtract them some way? Well, good job, guys. If I take dy dt and divide it by dx dt, what happens? That's really smally. Dy dt times dt dx multiplied by the reciprocal. That gives you dy dx. Hooray! So if you want to find dy dx of a parametric equation, you just take your derivative of your y's, we'll call it y prime of t, and divide it by your derivative of your x's, x prime of t, or dy dt over dx dt. And we will get dy dx. All right, so let's go to the second page. You're looking to find dy dx and then find it at a specific location. And then the question is, what direction is the graph moving? And when I ask you for direction, it's like up, down, left, or right. All right. Well, all we have to do is take the derivative with respect to t of x and y. I'd get dx dt equals 2t. I'd get dy dt is equal to 2t plus 6. Therefore, dy dx will equal 2t plus 6 divided by 2t. All I need to do now is plug in a t value to get dy dx. Let's do t equals 1. I would get 2 plus 6 is 8 divided by 2, which is 4. That means the slope of the tangent of this graph of this parametric equation is 4. Now, from this information, can we tell which direction this parametric equation is going without using our calculator and graphing? Nod your heads yes. Yes, we can find it. Okay? It's simple. dy dt will tell us if we're moving up or down. If dy dt is positive, I'm moving up, right? How are my y's changing at the specific moment in time? If dy dt is positive, that means my y's are going up. If dy dt is negative, my y's are going down. Bad circle here. Uh-oh. Oh no. This is bad. Shouldn't have been critical of the circle. Okay. dx dt will be telling me if I'm going left or right. If dx dt is positive, I'm going to the right. Which direction is my graph moving for x equals t squared, y equals t squared plus 6t plus 5 when t is 1? Up and to the right. 8/2, I'm going up, I'm going to the right. So up and right. You now can look at derivatives and be able to see direction. Okay, why don't we do number 3? Okay, we get a slope of the tangent of 16, and again, I'm moving up and to my right because dy dt is positive and dx dt is positive. All right. Let's move on to number 6. Let's find the equation of the line tangent to this when t is 2. Remember, for your tangent line equations, some of you forgot, you need a point and a slope. Slope should not involve variables. Slope should be a number. Okay? So I need a point. Now, a point is still going to be an xy, but it'll be at a specific time. And then you'll need a slope, which will be your dy dx at the specific time. I'm just coughing and sneezing all over the place. Okay, so go ahead and find your point and find your slope. And plug it in your equation. So 12 minus 4 is 8. 4 plus 1 is 5. Giving you y minus 4 equals 8/5 x minus 5. And we don't need any direction, starting point for our tangent line. It's just a line that will be tangent to this parametric equation. Okay? Now, let's look at second derivatives. Immediately with the second derivative, so back in your notes, it's not as easy as dy dx. So write that down. Okay? We know dy dx is, dy dt, which is easy to find, divided by dx dt. Well, the problem with dy dx and just taking the derivative again is that I have t's in whatever my dy dx is now with the parametric equation, right? Well, if I take the derivative of this, I'd have to take the derivative with respect to t to be able to work with these t's, or else it'd be a lot more complicated. So all of a sudden, if I tried to take the derivative with respect to t of dy dx, I would have d squared y over dx times dt, which is not what I want. I want d squared y over dx squared, right? But I can do something to this right here to give me that. Can anybody figure this out? What I need to do is multiply the bottom by dx and then have that so that dt can be canceled so that I have d squared y over dx squared, so the dt's going away. Well, can I get dt over dx somehow? What can I do, Mr. Darnell? That's exactly right. I can actually take this derivative of dy dx and divide it by dx over dt, and all of a sudden I get d squared y over dx dt times dt over dx. Those cancel, those multiply together to give me that. What does that mean? What do I have to do, Mr. Mester, when I'm finding the second derivative? It means you're going to get your dy dx, and you're going to take the derivative with respect to t of your dy dx, but you have to divide that by dx dt. Okay, so translation of that mess here is take the derivative of your first derivative, but divide it by dx dt, and that will give you your second derivative. Okay? So let's go ahead and practice that. Let's find the second derivative back to your examples from your second page. Find the second derivative at t equals 1, and then discuss the concavity of your parametric equation. Number 1 for your second page was t plus, wait. Oh, there it is. T squared and t squared plus 6t plus 5. Good. Number 3 was root t. And then, okay. Let's go ahead and find the second derivative. So if you have space to the right, let's do our second derivative. So you already found dy dx, right? Dy dx was 2t plus 6 over 2t. Well, now we have to take the derivative of this and then divide it by dx dt. Well, before I take the derivative of this, I'd have to use the quotient rule. I'm going to simplify this by dividing both terms by the 2t, giving me 1 plus 3 over t. That's going to be a little bit easier to work with. Now I'm going to take the derivative of this with respect to t. This gives me d squared y over dx dt with dx times dt. So again, this is 3t to the negative first. This will be negative 3 over t squared. This is d squared y over dx dt. I need to multiply by dx and get rid of the dt in the denominator. So that's why I divide by dx dt, which is just 2t. I like to put it as 2t over 1. I like to combine things. Negative 3 over t squared times 1 over 2t gives us negative 3 over 2t cubed. When t is 1, I get negative 3 halves. What does that tell me about the concavity of my parametric equation, t squared and t squared plus 6t plus 5? It's going to be concave down. Okay, go ahead and do this for number 3. Find the second derivative at 1, discuss the concavity. Question, Mr. Ramanetti? No? Again, I simplified it so that I don't have to do the quotient rule or anything crazy. If you did do the quotient rule or the product rule, you'd still get the right answer. It's just going to be a very, very messy derivative. But if you're finding it at a point at a specific time, well, you could still have a messy answer and plug it in and get a nice answer, you know? You get 24t squared plus 8t as your second derivative. I could plug in 1, I get 32, concave up. Okay, any questions about that? It's a little labor intensive, and it'd be even more labor intensive if you did not simplify this first derivative.
After you simplify the first one,
Yep.
you take that derivative, right?
Oh, I didn't take that derivative.
Yeah.
I did that mistake. That'll change everything. So 6 times 3 is 18. 2 over root t. And then that would be divided by 1 over 2 root t. This is d squared y over dx dt. This is dx dt. Dx times dt, this is dx over dt. This is dy dx, this is what you want, but we can simplify this. Giving me 36t plus 4. Plug in 2 or 1. Let's just plug in 1. I get 40. We're definitely concave up. Okay. Don't forget to take the derivative after you simplify, Mr. Messner. Good. Moving on, we'll be able to find locations of horizontal and vertical tangents to these parametric equations. If we remember, horizontal tangents are when dy dx is 0. Well, if I have a dy dt and a dx dt, which one would we set equal to 0? For a fraction to be equal to 0, what's the only part we have to worry about? The numerator, right? For a fraction to be 0, I just have to worry about the numerator. Well, the numerator, we remember, is dy dt for a parametric. As long as dx dt isn't also 0. Vertical tangent is when dy dx is undefined, or when the denominator is equal to 0. The denominator is dx dt for parametric equations. Just make sure your numerator isn't 0 as well. Okay, so go to page 3. You're asked to find the locations of horizontal and vertical tangents. All you have to do is take the derivative of x, take the derivative of y with respect to t, set them both equal to 0. If you find solutions, that'll give you either horizontal tangents or vertical tangents. at all those locations. That's vertical tangents.
Can you explain why that's
Right, dy dx. If I'm not moving at all left or right for dx's, but I am going up and down, so my slope of my tangent is all dy and 0 dx, up and down, no left and right, vertical. If there is no dy, there's no y movement, I'm not going up or down at all, but I am moving right or left, well then we have our horizontal tangent, right? Flat versus vertical. And we used to do these with, implicit equations when we're those crazy curves having horizontal and vertical tangents. You guys remember implicit derivatives? I'm sure you do. Okay. And then dy dx, if you want to, let's say it would just be 2t minus 4. Okay. Go ahead and tackle 10 as practice. Solving these equations with trig functions. We're going from 0 to 2 pi. Should have had like 3t plus 2 cos t. No, that wouldn't have worked either. I don't love these problems, but that's okay. All right, Mr. Romanetti, what is dx dt equal to 0? Mr. Romanetti. Yeah. Okay. All right. Now, Mr. Romanetti, the real one. When is dy dt equal to 0? Yeah. That's easy enough. Make sure we're ready to solve sine of t is equal to like -1/2, right? Or cosine of t is equal to, √3/2. So next year I'm going to switch up this problem. All right. So 0 and pi, are those going to be horizontal tangents or vertical tangents, Ms. Parihar?
Horizontal. Vertical.
Which one?
Horizontal. Vertical.
Oh my goodness. It's the bottom. If the bottom is 0, are we undefined or are we 0?
Undefined.
So does that mean I have a vertical tangent or a horizontal tangent? That's a vertical. Okay, good. So yeah, it's kind of tricky, I guess, with these parametrics. And then this will be the horizontal. Okay. All right. Extra problems. Put these in your notes. These are good problems to have us prepare for our quizzes and tests and stuff like that. What is the rate of change of y with respect to x of a particle with a position? X of t equals log t plus e to the 2t, and y of t is equal to root t squared plus 2t. And why don't we say when t is 1? This is more derivative practice. Do we remember our derivatives rather than something that's too crazy difficult? Of course, we know rate of change of y with respect to x just talks about dy dx, slopes of tangents. What is the slope of the tangent of this at 1? Well, go ahead and find the derivatives of the top and the bottom. Divide them, 1 and 1. Anybody else get that? Or a version of that? 2 over root 3 times 1 plus 2e squared is also a way you can write it, or you can distribute the root 3 to root 3 plus, and you can also, rationalize things. Root 3 over 3, 2 root 3, all sorts of stuff you can do. Let's not get into it, okay? Cool. But just find your derivative. Make sure you divide dy dt by dx dt to get dy dx. Next, what direction is a particle moving? Is the particle moving when its position is 1, 0, given the direction or the position of the particle is given by these parametric equations? X equals 5 minus t squared, y equals 2t minus 4t. 2t squared minus 4t. Okay? When the position is 1, 0, so they're not giving you a time, they're just telling you when the position is 1, 0, what direction are we moving in? ideas for what we can do here. Are you already working on this? What are you doing if you're working on this? Mr. Anson, what are you doing? You solve for... Perfect. We can figure out what time it is when our position's at 1, 0. So it should be at a specific time. So like, when is 5 minus t squared 1? When is 2t squared minus 4t 0? We're looking for the specific moment in time. It's just one moment, t equals one number, that makes this true. This will be when t is plus or minus 2, right? That's for the top guy. For the bottom, you factor out a 2t, and you get 0 and 2. Well, that means we're talking about time just 2, because that's when our x position will be at 1 and our y position will be at 0. So I found the time. Now I can just find dy dt at 2 and dx dt at 2. That'll tell me if I'm going up, down, left, right. Man, I was really looking for a negative value here. That's okay. Okay, dy dt up and down, dx dt left and right. Going up and to the right. Oh. All right. We did it. I'm moving left. All right. Last problem. Our toughest problem. We're going to need a calculator for this. Not even sure if this works out. We'll find out. X is log of t plus 2. Y is e to the kt. The line y equals 6x minus 3 is parallel to the line tangent to the graph of x comma y when t is 1. Use your calculator to find k. It's always good to set up what I'm trying to look for, you know, like what I'm trying to do, how I'm going to tackle this problem, and then do it. What am I trying to do? And try to find k. Good. Okay. How am I going to get k? It's when what occurs? When dy dx, when t is 1, equals what? Six. Thank you, Mr. Anson. Fantastic. So when dy dx, when t is 1 equals 6, we'll be able to get this. I'm going to do this rest of this problem right now. My advice is to watch it to prepare for your quiz. Okay? Sweet. Or if you want to stick around, I'm going to do it right now. All right. This will work out. I have to use my calculator to graph and solve. I will get a value though. (3k) e to the k should be in y equals. Equals 6. Thinking a very small decimal, not too small. .852 ... That's it.